Hello, Algebra students. This is our fourth lesson from this unit on exponential functions. The name of this lesson is Understanding Decay. And to get us ready for this lesson, I've got our warm-up here on the screen. Go ahead, pause this video. There's not really like a correct or incorrect answer. It's just asking you what you notice. And do you have any questions about the two tables below? Go ahead, pause the video and try that warm-up question now. All right. Before we jump into that warm-up question, I do want to point out the reminder over here to make sure you are checking your school email and your grade tracker regularly. The school email, the school's expectation is, especially if you're a virtual student, that you are checking that every single day, since that's one of the main ways your teacher and school staff will communicate with you. The grade tracker, if you are a virtual student, you should have received via your school email after the first assessment you took, and I continue to update that as I grade more of your tests and benchmarks to reflect what your grade is as we move through the class. So make sure you're checking that, especially after I've graded a benchmark or the midterm, because it will update with your new grades. Looking at our warm-up question, again, it's looking at these two tables, anything you might notice from the table or questions you have. In the past, when I've asked this question to students, one of the things students first notice is this first table is increasing, and it's increasing in a pattern of adding 1.5 every single time. I've also had people describe that as 1.5. Either of those are good. Because we notice it's adding the same amount every single time, we can use that to identify what type of relationship it is, if it's linear or exponential. And because it's going up by that constant amount, that makes this first one linear. For the second table, some of the other things in the past that students have noticed is that it's not going up by a constant amount. Here, you would have to add 1 to get from 2 to 3, but clearly looking at the rest of the table, I'm not adding 1, right? And so we can tell it's not going up by the same amount, which means it is not linear. Now, to identify it as exponential, we need to be able to specifically say there's that constant factor, that growth factor, where you're multiplying by the same amount every single time. Sometimes when I ask that question, what do you wonder? I've had students ask, well, I don't know like what this second pattern is. I can tell it's not adding something, but especially with these fractions and a 2 to a 3, sometimes it's hard to identify if it's multiplication, and if it is multiplication, what you're multiplying by. I do think it's actually maybe a little easier if you look later on in the table to get from a 9 to a 27 or a 27 to 81. We're multiplying that numerator by 3. And then to get from a 2 to a 4 or a 4 to an 8, you're multiplying that denominator by 2. So if you had a harder time identifying this pattern, it's because you're multiplying by a fraction. To go from a 2 to a 3, you're multiplying by 3/2. Or again, in the past, I've had some students describe that as a decimal 1.5. So both of these patterns involve that 1.5. This first one is just adding 1.5, making it linear. And the second one is multiplying by 1.5 or 3/2. And because it's multiplying by the same amount each time, it makes it an exponential function in an exponential pattern. We started our warm-up here, again, with this review of linear versus exponential, but also just having that reminder that you can add decimals and fractions, and you can multiply decimals and fractions. In our lesson today on new exponential relationships, we're going to see that multiplication with a fraction. Jumping into today's lesson, the goal for this one is to create and interpret equations representing exponential decay. Now, we have not seen this word decay yet. In class, I usually ask, like, what do you think of with decay? Some of the words, like decay is like something that's rotting, right? Or it might be something that's breaking down. And so let's keep that in mind. I don't know if our problems are going to be about things rotting, but this idea of like something breaking down maybe. and how that relates to our conversation about exponential functions. To get us started, this question right here isn't an algebra question. This is actually something I teach all the way back in developmental math. But this is how we're going to start this lesson. This idea that Diego has $100 and spends 1/4 of it. The question is, how much money would he have left? Go ahead, pause the video here and try this problem. I will say there are multiple ways to figure out this answer. And so if you really want to spend some time thinking about it, see if you can approach it multiple ways. Come back to the video when you've got an answer. So as I mentioned, there's a couple different ways you can approach this problem. One way is to start by figuring out how much money you spend, or how much money Diego spends. We know he spends 1/4 of $100, but we need to know what 1/4 of 100 is. And all the way back in developmental, I teach that if you're trying to find a fraction of a number, finding a fraction of a number is the same thing as multiplying that fraction by that number. So I need to do 1/4 times 100. 100, it actually helps to make look like a fraction when you're multiplying fractions. 100 is the same thing as 100 over 1. And when you multiply going straight across, 1 times 100 is 100. 4 times 1 is 4. And 100 divided by 4 is 25. So that helps me know that he spent $25. So if he spends $25, to find how much money he has left, I'm taking my $100 and subtracting $25 to figure out that he has $75 left. To get that answer, there's 2 steps I'm doing, right? My first step is I'm figuring out what 1/4 of 100 is. And then my second step, I'm using subtraction here to figure out how much money is left. I've taught this lesson a lot at this point, and I would say the majority of students, if they know how to do this problem, this is the math they're doing. They know 1/4 of 100 is $25 and take it away from the 100 to figure out how much money is left over. I did say, though, that there are multiple ways to do this problem, and this, while it does get us to our answer, isn't going to be the way that helps us with looking at the problems we're doing today. So a different way you can approach this problem is down here. When we are told that he spends 1/4 of it, what we were really doing was taking the $100 and taking out 1/4 of the $100. But to save us from doing that subtraction, another way to think of this is if he spends 1/4 of the money, that means the fraction he has left is 3/4, right? If you think about what you know about fractions, if he spends 1/4, then he has 1, 2, 3/4 of it left over. So instead of having to find 1/4 of 100 and then take it out to see what's left, we can jump right to doing only one step and thinking what 100 times 3/4 is. If we do that, we know he has $100 and he's going to have 3/4 of it left. And so similar to what we did earlier, I'm going to change 100 to a fraction, multiply going across, and then 300 divided by 4 is 75. This way, some students identify as being easier because notice there's only one step. The one step is doing that multiplication problem. You're just doing it kind of like with the opposite fraction. Some quick practice here with the fractions. I said he spent 1/4, so 3/4 is left over because there's a total of 4 parts. If I told you that he spent, let's make it weird, 2/7 of his money, what fraction would be left? Well, it's out of 7 parts, so if he spent 2, 7 minus 2 means 5 of those 7 parts would be left over. So it's some small subtraction problem there, right? But that gives you the fraction you would multiply it with. And this is also the way we're going to need to do our problems today, this idea of finding the other fraction. So to give you another chance to practice doing this way, there's one other story here. Go ahead, pause this video now and try number 2, doing a process similar to what we did above. All right, so this time we have a person who makes $1,800 per month, and we are told 1/3 of that goes towards her rent. So I'm taking some quick notes here. 1/3 of that money is her rent, which means 2/3 must be the money that is left after she pays her rent. So for my question, which two numbers can you multiply to find out how much she has left after paying her rent? I'm looking for what two things can we multiply to find how much she has left. Since I'm talking about how much money she has left, it means I want to use this fraction here. I'm going to take 2/3, that's the fraction she has left. I need to know what 2/3 of 1,800 is. This here didn't ask us to actually do that multiplication. It just asked what two numbers you could multiply to find that out. So this right here is really what we're looking for. If you did go ahead and do that multiplication, it ends up being $1,200 or $1,200. So to summarize here, the main idea of this first part is that a decreasing quantity can be expressed with subtraction or multiplication. So for example, when we had Diego with $100 and spending 1/4, or they're with that person had their paycheck, but they're spending some money, you can figure out those answers and figure out what's left over with subtraction or multiplication. But for today's lesson, with exponential situations, we have to be able to do the multiplication part. So no subtraction, just the fraction multiplied by the number. So to summarize this, using a variable this time, we've got, if I told you there were X dogs at the park and 1/5 of the dogs were on a leash, there's two things we can represent. We could represent how many of the dogs are on the leash and how many dogs are not on the leash using those two fractions. If we know 1/5 of the dogs were on a leash, that would mean 4/5 are not on a leash. And so if I wanted to find the number of dogs on a leash, I would want to take my 1/5 and multiply it by X. That would tell me how many dogs are on a leash. And if I want to know how many dogs are not on a leash, I'm taking that matching fraction, 4/5, and I'm multiplying 4/5 by my number of dogs. That would tell me how many dogs are not on the leash. We need to be able to do this multiplication for this problem, or for this lesson and the problems we're doing today. So let's jump into the actual exponential situations we're going to be looking at. The main focus of the rest of this lesson is on the value of a vehicle. So our story says every year after a new car is purchased, it loses 1/3 of its value. This is not true for all cars. This is just the story we're working with. So the specific car in the story is going to lose 1/3 of its value every year after you buy it. And let's just say that the new car costs $18,000. The first thing I'm going to have you do is write out what math we could do to find the value of the car for each year in this table. So for example, after year 1, if I wanted to find how much that car is worth, if it loses 1/3 of its value, do you know what expression we could write, what math we could do to find that answer? Well, it's related to what we were doing above. If I know it loses 1/3 of its value, that means I'm going to say the remaining value. Let me write the word value too. The remaining value is 2/3. Those are kind of like those two fractions that have to go with this story, similar to what we were doing above. So if my table is showing the value of the car, it means the fraction I'm going to be using is this one. My table isn't talking about how much money the value loses. It's asking how much value remains. So to figure out the value of the car after 1 year, I would want to take the $18,000 and multiply it by 2/3. That would tell me the value after 1 year. So we have years 2, 3, and 6. I'm going to have you write 3 more expressions. The reason we're using the word expression is because I don't need you to calculate these. I don't need the answers. I just need the math problem we would need to do to find these. Go ahead, pause the video, and try years 2, 3, and 6. All right. To get to year 2, remember, I don't need an answer from year 1. Uh, for year 2, I know we're starting at a value of 18,000, and it's losing two-thirds of the value is remaining after 1 year, and then two-thirds of the value is remaining after 2 years. If you did get an answer for this first part, I'm going to put it in red. Remember, we said this isn't necessary, but if you got an answer here, the math you would be doing for year 2 is just taking year 1 and multiplying it by two-thirds. But instead of writing the 12,000, we're writing this part right here again to show we're taking year 1's and multiplying it by two-thirds again. If you did not get that earlier, it's okay. Do you think you have an idea now for year 3 and year 6? For year 3, we've got the $18,000 we start with, and two-thirds is remaining after year 1, two-thirds is remaining after year 2, and two-thirds is remaining after year 3. And then for year 6, again, notice we're making that jump there. For year 6, I can keep doing what I've been doing, or there's an easier way to write that. Every single time, notice I'm taking 18,000 and I'm multiplying it. I'm going to switch to the multiplication dot. I'm multiplying it by two-thirds. How many times am I multiplying it by two-thirds? Well, once for every single year. So for year 6, instead of writing times two-thirds, times two-thirds, times two-thirds 6 times, I can just say times two-thirds to the 6th power. And I can even rewrite these other ones using exponents as well. This one here, I'm multiplying by two-thirds to the 3rd power, or two-thirds cubed. For year 2, I'm multiplying by two-thirds to the 2nd power, or two-thirds squared. And then here I can even rewrite this one. I'm multiplying by two-thirds to the 1st power, which means just multiplying it by 1 time. So then to summarize this pattern, we get to year t. If I don't know how many years have gone by, but I want a way to express how much of that value remains after t years, the pattern here is every single time we take our 18,000 and we multiply it by two-thirds, I just multiply it by two-thirds t times. Every single time, the year was the exponent. The year was the exponent. The year was the exponent, which is why we have our exponent t here. Now, what I've got over here is not exactly an equation. To make this an equation, I could just say 18,000 times two-thirds to the t power. That would equal, let's use v for the remaining value of the car. Now it's an equation. Looking at this table here, this is how we had started the, lesson 2 off when we were talking about exponential growth. This is still an exponential relationship because I've got that variable as my exponent. The value of the car is just doing something different than what we saw with exponential growth. When we look at this problem here, the value of the car, we know it's losing value. So here, that exponential part, the part we're multiplying, isn't making the value increase, it's making it decrease. When we had talked about exponential growth, we had called that number you were multiplying the growth factor. But here, it's making the value go down. And so instead, this number we're multiplying here, the two-thirds, has a different name. We call it the decay factor. That word decay is talking about how this value is going to decrease. I had said sometimes I hear students think of the word decay and think about something breaking down. I use those words breaking down because you might hear, food is rotten and decaying and breaking down. Here, the value of the car is breaking down. It's decreasing. The reason that multiplication above made it decrease instead of increase is because we're multiplying by a number between 0 to 1. We looked at exponential growth for 3 lessons. And in a lot of those situations, we had talked about things maybe doubling and multiplying by 2, or tripling and things multiplying by 3. In the warm-up, right, that table that we had looked at, you were multiplying by 1.5. And there's no word for that, but for all of these, the value or the amount is going to increase with time. Even if you multiply by 1.5, it's still going to keep going up. But when you start multiplying by something less than 1, like in this problem here, we were multiplying by 2/3, that's going to make the value decrease because it is less than 1. Be careful with those fractions. Just because it's a fraction doesn't mean it's decreasing. For example, that 1.5 there, we had also talked about how you could see that as 3/2. I know in one of the previous homework problems, you were multiplying by 5/4. 5/4 is equal to 1.25, so that still would be increasing. But when that fraction value is less than 1, if you divide 2 by 3, you get 0.66666666. That's less than 1. That means it's going to decrease. And so that is what these final 2 lessons in this unit are going to be all about, is understanding exponential decay when something is decreasing. Above, I had given you the information and you wrote an equation. Just like we did with exponential growth, we want to be able to go both ways. So our goal for today is to be able to write an equation and interpret an equation. So on the screen here, I have a different equation. And this time, I'm giving you this equation and asking you to tell me what these 2 numbers mean. Pause the video now to read through the story and try answering this question here. Remember, pausing the video and trying these is super, super important because it's a great way for you to get that practice before you do the homework and take a test. So pause this video now and try. All right. To help us out, I put that first equation up here as well, just as a reminder, because we can compare this equation to this new equation to help us make sense of what each of those numbers means. Starting with the 10,000. To understand what the 10,000 represents, it might help me to think about what the 18,000 represented earlier, or with our exponential growth equations too, because this number always is telling me the same thing. That number is telling you where it starts at. So specifically here, it's telling me that starting value of the car. So I could say for this car starts at a value of $10,000. That is what that 10,000 in the equation means. And then the other number, the 4/5, again, think about what the 2/3 means here. Now, a common incorrect answer is that 4/5 is the fraction of value the car loses. And that's incorrect because think about what the 2/3 was. In that problem we did together, the fraction I see is not how much it loses. 1/3 was the value that it's losing each year. The 2/3, the part you see in the equation, is the remaining value. Since this equation is about the value, we're using the fraction that represents the value that's still there. So similarly down here, the 4/5, because this equation is telling me the value of this car, 4/5 is that value that remains each year. Ooh, that word remaining looks a little messy, but the value remaining. So we're going to take it one more step further. If we know 4/5 is remaining, if I want to say what fraction it loses each year, what fraction would it be losing? If 4/5 is remaining, that means it loses 1/5 of the value. Again, I'm doing that subtraction problem. It's out of 5, so if 4 parts are remaining, 1 part is what it's losing. So here for the 4/5, I could say 4/5 of the value remains each year, meaning the car loses 1/5 of its value each year. And so that is our interpretation of that fraction 4/5. The goal for this lesson is that we're able to do both. That if I give you a story, that you're able to come up with the equation, but also if I give you an equation, you know what the story is and you know what those two numbers represent. So to summarize what we had talked about in this lesson really makes the switch from exponential growth to exponential decay. So in this lesson, we were talking about quantities that decrease or decay by the same factor repeatedly. We had looked at this one about the car just now, where the car is losing value over time. And then there's this example here that we are going to wrap up this lesson with. So suppose a digital camera worth $400 loses 1/3 of its value each year. If we wanted to know the value of the camera after 1 year, I need to know what fraction of the value remains. So if 1/3 is the fraction that's lost, it means 2/3 remains. So to find the value after 1 year, I would take 400 and multiply it by 2/3. If I wanted to know the value after 2 years, I'd be taking 400 and multiplying by 2/3 twice, one for each year. And so the reason we had started off this lesson talking about how you figure these out with multiplication and not subtraction and multiplication is because when it comes to exponential equations just have multiplication in them. If you think about how we would represent this equation here, I'm going to jump down to the bottom. The value is starting at $400 and multiplying by 2/3 every single year. And so I would use the value t for the number of years. When you write an exponential equation, there's no subtraction in it, just multiplication, which is why we needed to learn how to do that math with multiplication. And when you only use multiplication, why don't you see the 1/3 in this? Well, because 1/3, we said, is the value that's being lost, and our equation is about the value that remains. V would be the value of the camera. And so it makes sense to use the fraction that represents the value of the camera. And so that's where we get that 2/3 from. So our final question, the cool down, is here on the screen. It is about the depreciating phone. Depreciating is a word you might see for when something loses value. Pause the video and try these questions here. This will be a great way for you to check in and see how you're doing on this topic. Come back to the video when you've got answers for number 1 and number 2. Right, hopefully you went ahead and tried this problem here. The first thing I would do is I'd write out both of the fractions just so I have both of them. I know it's losing 3/5 of the value, so that must mean that the remaining value is going to be 2/5 there. And so after 2 years, if I want to know how much of the value remains, I'm taking that starting amount, the $800, and I'm multiplying it by 2/5 for the first year and then 2/5 for the second year. You could have written it like this, or you could have said 800 times the 2/5. And since there's 2 of them, I'm squaring it. When you go to do that math, that means we need to do 800 times, that's going to be 4/25 there. When you go to do that multiplication, I'm going to go ahead and simplify this, I think, and say that equals 3,200 over 25, and then that is $128 for the phone after 2 years. So we see it lost a lot of value, but notice it's losing 3/5 of its value each year. 3/5 is over half of its value. So if it was losing half its value each year, after 1 year, it would be $400, and it lost even more than that. So it makes sense that my number's a lot smaller than what we started with. Number 2 is asking us to write an equation for the value of the phone. We're calling the value of the phone T years after it was released. So for this one here, my value of my phone is going to equal the $800 it starts with. And then we are multiplying by the fraction that represents the value of the phone after each year. That's 2/5. And then I'm multiplying 2/5 every single time a year goes by, so that would be t times for the t years. This equation right here would represent the story, and is an exponential equation. This is just going to be an equation representing exponential decay. I know that value would be decreasing because this number here, my decay factor, is less than 1. Thank you so much for watching this video. We are going to continue to talk about exponential decay in the final lesson for this unit, tomorrow's lesson. So make sure you check that one out as well. Thanks so much for watching. See you in the next one.